constructors are methods which are necessarily linked to implementation. So some people have been writing, I've noticed in the notes, the danger is that constructors leak information about construction and implementation. That's not actually the problem. It's not as though we're trying to keep things secret. People could find things by looking in the source code. The example I gave of the Amazing Turk was just to show you that the implementation was closely linked to the function. So just showing you there's a connection between implementation and the function signature. So it's not giving us the abstraction we want. And we want that abstraction not to keep it secret. We want that abstraction so things aren't coupled. So we're not bound to particular implementations. We're not bound to particular classes. We only want to be bound to type. So we talked a little bit about constructors and why they're not in interfaces and why you can't inherit them. We talked about having construction methods. And now we're looking at an actual design pattern called the factory method pattern. And remember, we looked at a maze last week. And I'll just go through that code. And I guess we should do a super quick revision of what the factory method is before we jump into the code, because you might have, it's a crazy thought, but maybe you haven't spent the whole time between now and the last lecture just repeating those last 5 minutes over and over in your head, waiting for me to come along and finish them off. So let me just give you those 5 minutes again, but really quick. A factory method gives you an interface for creating an object, and then you subclass the client and override bits of things, and Richard explains very badly. You have a client which needs some products, and we don't want the client to actually know what class the products are, some other object it's going to use. We don't want it to know actually what class those objects are. We want to have this abstraction thing. We want to be programming to an interface. So we can't use a constructor to create them because that locks us into a particular class. So instead, we tell the client who needs these objects to use a method, a named method to create them, and the method creates something. The type signature of the method returns a type, so it returns an interface, an object of an interface. So that from the type signature of the method, we get no clue as to the actual class we're going to get back. We just know what family it's going to be in, which is good. That's given us the break we want. And then how do we actually implement the method? Well, we can't write a method that returns something that belongs to an interface. Yeah, you can't say new interface name of something. There's no constructor for an interface. So we actually need to construct a concrete class. So we make actual methods which return actual instances of concrete classes, and we use inheritance to determine which of those methods we call. Okay, and here's the example of in pictorial thing. Let's look at it pictorially. View the image, make it really big. No. View it in a page and make it really big. Oh yeah, really big. Here we go. So we've got the product that we need. Well, the things on the top here are the abstract things. And you've got something that creates the product. And it has a factory method and it has some other operation. And this line I think is going the wrong way. And then here's some actual code that tells you a possible implementation of it. And this is actually an implementation of an operation. So when an operation is running, it needs an object, it needs a product. So it calls the factory method. So we make sure we create it by using a named method rather than using a constructor. And only the factory method uses a constructor. Yeah. So this gives us, so far it looks like we've just done naming changes. Instead of calling a constructor, we're calling a named method. And the named method calls a constructor. But the advantage of this is we now can create children of the creator. Oh, that's sort of biblical, isn't it? And those children can overwrite the creation function to do whatever they want. So an operation doesn't have to be implemented in all the children. All the children have to do is override the actual specific instance of the class in the creation function that's returned, and then everything still works. So this is an example of the template function method pattern. Remember the template method? You've got some method in the parent, and it calls some functions, and the kids override the functions, and that changes the behavior of the method in the parent, because the method in the parent, when it calls the functions, now gets the kid functions rather than the parent functions. And remember, we talked about that's sort of backwards to how you expect. You'd expect the parent function would always get the parent functions, but actually, if a kid overrides the parent function, when the parent function runs, it gets the kid's function. Okay, so that's the template method. And that's a template method pattern, and the factory method is the name of the overridden method that is overwritten in the child to let us create the object. That's the longest phrase I've ever said without a full stop. Yes?
what's the advantage of having like an inheritance concrete creator rather than having like concrete factory methods in the creator? You know what I mean?
Ask the question again. It's probably a really good one because this is a slightly unfamiliar. When you first see this, it does seem to be doing more work than you need. So ask the question.
Like, is the creator an interface?
Yep, the creator is an interface, or it could be.
Yeah.
That's the idea, but in practice, when you implement this, often it's a whole lot of work to set up an interface and then write a creator. If you've got a creator, you're going to be using 90% of the time. Oh, sorry, no. The creator's, no. We're going to have to restart, okay? Because I answered that wrongly. To be really neat, it's quite good if this is an actual class, because then it can implement this function here, an operation.
Yeah, but is it like, and then what I was saying was, is it because the concrete creator inherits the creator?
It extends the creator, yep.
Overrides factory method.
It overwrites a factory method, so now when an operation runs, it uses this one.
Yeah.
Yep.
Is there any like, okay, so you wouldn't really want to have different factory, rather than having a factory method, having concrete methods which create the concrete class.
Are you saying have a range of construction methods up here
Yeah.
and select between them?
Yeah.
We don't want to do that because our idea is when we write this, we don't want to limit ourselves in the future, anticipating these are all the classes I'll ever need to create and here's an if statement selecting between them. Because that's now tying this class here to those other classes. We've named those other classes in this class, so we've got a dependency to them. So tomorrow you can't think, oh, there's a new one I'd like to add, because now you've got to rewrite that class. So they're tightly coupled. Or if this was released in a library 6 years ago, and now you want to do something cool and new with it, you can't, because you've just thought of something new that the creators didn't envisage. So the idea is this lets us do things that the creator didn't think of initially, which fits in really nicely with our idea of incremental design. Because yeah, if you design everything perfectly up front, yeah, you know everything you ever need to do. But that never happens. Yeah. Things change, there's change, and things you didn't envisage come up, and this lets you add new things just by subclassing it with a new thing. Let's look at it concretely with the maze code, so you can see what actually happens with the maze code. And the pain here is we need to do some subclassing, and as you know, that's a bit of a sniff anyway. Here's the maze. So here's our first way of running the maze, and we saw this yesterday. We're looking at the client thing, the one in the middle in that last picture. Actually, let me open them both at the same time so I can flip between them. So we're now looking at this guy up here, the creator. Here's the code. I'm going to make it smaller because that's just so ridiculous. Can you all still read that? How about that? I can go more actually. How about that? Oh, fantastic. Okay. Here we go. So here's our code. We've got the class. It's building the maze. It's doing all the connections. And up here, it's making rooms and doors. So this class is linked to the room class and the door class and the wall class because it names these classes and it uses their constructors. So if you want to change a door to be a magic door or an exploding door or a crazy hyperspatial dimension tube door, you can't. You can write a new door class and then you're going to have to recode this to refer to the new door class. So that's a real pain. So this is tightly coupled. We don't like this solution. But make sure you look at this solution and understand how it works because all the other ones are just going to be variants on this. And these variants are going to be more code, so it's going to look more complex, but it's going to give us more flexibility and ability to adapt with changes in the future. All right, here we go. So that was our first one. Now let's look at using a factory method. Here's the maze class. I've commented out the old lines that used to be in there and written the new lines underneath. The only change we need to make is quite trivial. We now use named construction functions rather than constructors. And also, we define them in here. Now they're returning maze, room, wall, and door. There's no reason maze, room, wall, and door couldn't be an interface. In this case, I just made them a class, and I'm thinking if I have another door, I'll subclass door to get the other door. But if you really didn't want to use inheritance to create your whole families of doors and all the different doors you could have an interface called the door interface, and then you could have something called the default door, which implements the door interface, and then this would say, give me a new default door. Yeah, this is a sort of default thing happening here. This is what we get for default. Okay, so that all looks familiar. But the advantage of this is now, without changing this class, we can come up with a new maze that uses a different sort of door and a different sort of wall, and we get to reuse all this code and all the connections and everything without changing anything. So let's go and have a look at that. We might want to change a maze into a bombed maze, and a bombed maze has potentially a bomb in each room, and when it goes off it damages the walls, and you can have bombed walls, and there might even be, no, they've just got normal doors. Okay, so it's just like a normal room, but it has some extra properties. I'm not actually showing you the room class and the bombed room class, but you could imagine you'd have a maze which might be made of bombed rooms, which are rooms which potentially have bombs. It's a very violent example, isn't it? That's what happens when you stand on the shoulders of giants. Giants are bloodthirsty beasts. So we're just going to look at this here. Here's the bombed one. Look how it works. This is all we need to do to make a bombed maze game. We just say the bombed maze game extends the old maze game. I've got a capital letter problem there in the maze game. And all it does is override the constructors, the construction function, not the constructors, the construction methods, to use a different class. And now the parent class, which is in maze game, which had all the stuff that set up the maze and does everything, that's still there and that's still running. That belongs to this because we inherited from this guy. And so the same maze is set up, but now it uses different doors and different walls. So you could see, you could set up, I don't know, if you were playing Fury of Dracula, you could set up your map of Europe and you could work out all the cities and everything, and you'd have that set up. And then someone could say, I want to reskin this game. I don't want it to be Fury of Dracula anymore. I want it to be, someone did reskin it last year. What did they make it? Pac-Man. Someone did it, Pac-Man. All right, so you want to call it Fury of Pac-Man. Or the Hunger of Pac-Man. So what you do is you change cities into, I don't know what they, corners, and roads into hallways, and Dracula into Pac-Man, and Van Helsing into a ghost. You do make all these changes. You could do that with this. You can see you wouldn't have to touch the logic of the game at all. You just subclass Fury of Dracula and you'd call it Fury of Pac-Man, and you'd just override a few creation functions along the way, and then the whole nature of the game would change. If you'd set it up right, so changing the creation function, so interchanging objects means everything still works. So the objects belong to the same class. So somehow the city and the intersection have to have a common interface. So your game logic that works from where you can go to where and moves people around and things can talk to both of them and work out what they're connected to. So yeah. Does that make sense? So you have, that's when you'd probably wish you'd program to an interface originally instead of cities, because you probably want city and intersection in Pac-Man. They're probably, but what's a more general name for that? It's probably just a node in a graph, isn't it? You probably want your map of Europe to be a graph. You probably want city to implement the node interface, and corner on a corridor to implement the node interface, and you probably want road and rail to implement the link interface, and now Pac-Man corridor would implement the link interface. Yeah. And now you've got this completely flexible game. You can reskin it in a few seconds and everything still works, and your test cases still work, and you don't have to retest everything. Everything's good. Does that make sense? So that is the factory method. So it's pretty cool. But you might not like it, because maybe you don't like subclassing, and maybe you want to be more general. Well, another approach is, rather than saying, all right, I've got something that creates a maze, and now I want to have something that creates a slightly different maze, that is more or less the same, except for some functional element that I want to change. The first method we thought was, okay, we'll just make this new thing inherit from the old thing. We'll pick up most of the stuff from the old things, and we'll override creation functions in such a way that this guy still works. That's one way of doing it. But another way of doing it is saying, okay, well, let's say this guy no longer creates the objects, so we don't have to subclass him. Let's say this guy delegates the work of creating the objects to some other object. So he does all the game logic and sets everything up, but there's some other object over here that builds the doors and walls for you. And then you can see I can use this same guy, I don't have to subclass him, use the same guy, and instead of passing in an object that builds doors and walls, I can pass an object in that builds bomb doors and bomb walls instead. Or instead of passing in an object that builds cities and roads, I could pass in an object that builds corridors and intersections. Yeah. And as long as they all satisfy the same interface, and this object here is building things to that interface, and this client here expects that interface rather than a particular class, I can change the object that does all the building, and this guy, which is independent of what we've built, still works. Does that make sense? Now the guy that does the building, that's a factory. Yeah, making things in a factory. But it's not a factory method now. It's actually an object over here building it. So we call that a factory object or a factory class. And you normally make it an abstract thing, and then you make different instances of it to build the different sorts of things you need. So we call that the abstract factory pattern. So you have an abstract factory that builds what you want, and you create an instance of it to build Pac-Man worlds, and you create an instance of it to build Fury of Dracula worlds, or you create an instance of it to build mazes, or you create an instance of it to build bomb mazes, and it creates all the elements. And now, that's the hand-wavy version. Let's look at it precisely as code. Let's look at what the client looks like now. Client's a little bit different because it doesn't have to do any it doesn't have to have any creation methods. When you call the client to construct a maze game, sorry. No, the maze game it needs the maze. So when it builds a maze initially, it passes in a factory object. So instead of just creating a maze, it passes in a factory object. Or it gets passed in a factory object. Sorry, when someone calls create to create the maze, they give us a factory object. So now we're creating the maze, we just use that factory object to build everything. So instead of doing new like we used to before, we now call that object and we call the construction method in that object to build everything. So the factory object that gets given to us knows how to build the stuff. We don't have to have any creation knowledge. We've delegated that out to this factory. Does that make sense? And now it should be reasonably clear that if you pass different objects in, different factories, you build different stuff. And notice none of the other code needs to change, so everything still works. It's wonderful. We've decoupled the two. Does anyone want to ask a question about that? Does it not make sense? Because it's very, very beautiful. I want to make sure you got it. Yes?
I was just wondering that, like, you've got factory and that returns like the maze and the rooms and doors. Why not just have the factory do everything and return the whole game to...
Oh, yeah. Oh, that's a really good question. So I'm going to rephrase it and echo it out to everyone and see what people think. We'll talk around it. Why do we have the factory building doors and walls and windows, and then we've got our own method that builds a maze and connects everything together? That seems like a lot of work, and it is. Why don't we go to the way we initially had it, where it was all in one file? So one thing builds the maze, and it also builds the doors, and it also builds the windows, and it also connects everything up. Because we could do that, and that would be better in some ways, because it's certainly simpler. Do you want to have a hazard at guessing why?
Because you've still got everything talking to each other. Inside the factory. Inside
that one factory thing, yeah, you're locked to particular classes. Oh, I see. Are you saying why not have a maze factory?
Like a maze factory, so if you had a maze factory, you wouldn't ask for a maze and rooms and doors and then build a maze yourself.
Oh, I see. If you had a maze factory, why are you asking the maze factory to build doors for you, walls for you, and rooms for you, and then you're building the maze yourself? We don't have to do that. We could have a maze factory that builds maze, and it calls a door factory that builds doors and a... Yeah. We wanted to separate the two, though, because I had this idea. I'm just thinking of future change, remember, that all work now absolutely perfectly, and this one's actually slightly harder to code now, but remember we also think about the future and future change. I'm imagining that rooms, walls and doors can vary independently of the structure of the maze, so I'd like to have them encapsulated in different classes so I can change one without changing the other at all. Another example of that sort of thing is like, just a naive one, you could imagine you'd have a priority queue of student objects. You might also want to have a priority queue of ducks. And you could put them all together, but you can probably see the way of arranging the collection might vary independently of the objects in the collection. So it's quite nice to separate them in different classes. And then by composing them, you get all the combinations. Rather than having to write a single combined class for every combination, you'd get a combinatorial explosion of classes you'd have to write. So we quite like the idea of separating things that are different. But you're absolutely right. Probably to build the maze itself should go in a factory as well. Yeah, that's a great idea. Yeah. And then you could have a factory object that built a Europe maze, and you could have another factory object that built a China maze, and you can have another factory object that built a, Battlestar Galactica maze with different connections and different connectivity and so on and so on. And then using those different objects, you could then be playing the game and pass in a maze object, and suddenly you can play the same game with the same rules and everything, but you can play it on different topologies, in different worlds. And then you can reskin those worlds to look different and have different cities being different things. So you can change it in two ways then. Yeah. In fact, you could probably even imagine you could skin the rules. You have some sort of rule building object factory, and you could pass different rule men into it, and then you could play the game and modify the rules by passing different rule factories in. That's getting quite abstract now, so it's slightly harder to see. And there is, in fact, a pattern that does exactly that job that we'll see later on. Yeah. So does that answer the question? Yeah. Yes?
Why do you have the walls written that, like the new walls? Why can't you just make the really good make room or make walls?
Have I done something wrong?
No. The walls, see how you did the set side.
Oh, yeah, I've done something wrong. Thank you. What have I done wrong here? Should I be calling you wall? What sort of lunatic am I? That should be factory.makeWall. Yeah. Thank you very much. So my factory is hard-coded to build one thing. And I changed it to Pac-Man world, but instead of getting whatever we expect, we're getting walls still. It's really annoying. I'm in outer space, traveling around the galaxy, but there's walls floating around everywhere because I forgot to build the factory properly. Yeah, thank you. That was a deliberate error I put in there to make that really clear, so I'm glad you spotted that. Well done. Yeah. Okay, so that's what the client looks like. Now, can you guess what the maze factory looks like? And then what a bombed maze factory would look like? What's the difference between the two factories? They're both going to implement the same interface, though actually I was lazy. And, well, no, the person that I stole this from was lazy. This is the Gang of Four example. Well, I'm not saying they're lazy, but they actually implemented maze factory as a concrete class rather than as an interface, because I guess they wanted to have that being the default thing that happened most of the time. So to make other factories, you actually extend that one. And to be fair, they were doing this in the land of C++, and we're now in the land of Java, which does things differently. So if it was me writing it, I'd actually have this as an interface called maze factory, and then I'd have a default maze factory and a bombed maze factory actually being concrete instances of that interface. All right, so let's see what the maze factory looks like. Oh, I didn't mean to open it that way, did I? I meant to open it this way. Here's the maze factory. All it does is override the methods. It's, as you notice, irrelevant that it overrides the make wall function because we forgot to call it. But had we called it, that would... So this maze factory makes rooms, walls, and doors and makes the default version of each. And the bomb maze factory makes rooms, walls, and doors, but makes the bombed version of rooms and walls, though it still makes the default version of doors. Now, the reason we have a factory rather than doing this method by method is this is really convenient if you've got a class of objects that all need to be created the same. So it wouldn't make sense if we were trying to reskin it to Pac-Man and we had Pac-Man walls, but we had Pac-Man corridors, but we had cities at the intersection of every corridor. Cities of Europe. See, that wouldn't make sense. You can't mix and match them like that, so we didn't put them in independent classes. We put them all in the same factory. So that factory makes doors, walls, and rooms that go together, a consistent set of them. And another factory makes another set of doors, walls, and rooms that go together, a consistent set. So for chess, if you go back to our original chess example, if you wanted to create different... You might have toyed with the idea of having chess objects you created that could be displayed as tiny little images, and then you might have thought of having chess objects that could be displayed as, 3D vector graphics that you could rotate or something like that. So you'd like the rules of chess and all the things for working out if it's made in one and all the structure of the board and everything like that. You'd like to reuse the same code, but you might like your pieces to be displayed differently, have a different display function. So you might create a new sort of pawn called a 3D pawn. No. You might create a new sort of rook called a 3D rook. Out of my room. You might create a 3D rook and... Oh, I've so lost it now. You might create a 3D rook. Okay, and so you could have a game with a 3D rook or a game with a normal rook. And then you just pass the different rooks in to make the different games. But when you pass a 3D rook in, you've probably also got to pass in the 3D queen and the 3D king and so on and so on and so on. And if it's up to the client to get everything to match, they'll forget and stuff up. So you'd have a factory called a 3D piece factory. And you'd pass the piece factory in. That's a nice idea, isn't it? A piece factory. You'd pass the piece factory in, and it would build a rook, build a queen, build a knight, and so on, and they'd all be 3Ds, and 3D versions of them. And you'd pass a different piece factory in, a 2D low-res one, and it would create 2D low-res. So you see that all stay together? So that's the idea of a factory, that they're a family that you want, when you vary one, you want to vary the others, where they all vary together, so you lump them together in a factory. So things can vary in different ways, and we're trying to keep things that vary together in the same class and things that can vary independently in different classes, and this is just allowing us flexibility for change. Is that cool? Whew, that was very long to say all that, wasn't it? It's a very simple idea, but okay. Notice it involves programming to an interface, not an implementation. It gives you consistency amongst products. I said that with the chess pieces just then. Notice, though, that it has one difficulty, that adding a new sort of product is difficult. So if you wanted to vary the game by having a new piece called a squeen or something, none of your factories build squeens, and your factory interface doesn't have a make squeen function. So you're sort of completely stuffed. So you can't vary it in that way. You can vary the instantiations of the different pieces, but you can't vary which pieces the factory makes. So that's something, that's a way of, if you're expecting that sort of variation, then an abstract factory isn't the way to go. Here's an example now. I put my chess code up. I wonder if you can see, here's my code for the bishop. A bishop extends iterated step piece. So I had this sort of abstract class called an iterated step piece that you give it a direction and it can move in that direction forever until it falls off the board or runs into an enemy piece or one of its own pieces. And so a bishop is an iterated step piece, and I override the function legal directions to return step diagonals. So it gives it the 4 vectors for moving diagonally. Does that make sense? And then it will iterate over those. So this is all my bishop has to do, and now I've got a complete bishop. What pattern am I using to do this? Can you see I'm using one of the patterns here? We'll look at some more and we'll see if you can see. So that's what the bishop looks like. Here's the rook. It looks more or less exactly the same, except it overrides legal directions to return the orthogonals. You know, up, down, left, top, left, right. Here's the queen. It returns, legals returns adjacents, which is just orthogonals, union, diagonals. It's done somewhere. Out of here, in the step class. Here's the king. Okay, the king returns step dot adjacents for legal steps. It extends a different sort of piece called a one-step piece. It can move once in any direction that you give it a vector for, but it can't keep iterating that movement. So I pass in adjacents exactly the same as the queen, but because it's extending a one-step piece, it just moves one in each direction, unlike the queen who can then keep moving. And I override another function called isMatePiece to be true, to indicate that the king is a piece that's involved in checkmate. Other than that, it looks the same. Here's a knight. Knights are fancy. I actually had to create some crazy steps for the knight. Here are all the legal steps a knight can do. But again, it's just a one-step piece that overrides legal steps. And I didn't put pawn in because that's quite a weird one, actually, to do. OK. I'm using a pattern in my design. What pattern am I using? Oh, this was just a quick quiz. What's that? Someone said? Oh, no, it's not an adapter. Let me say in detail what's going, and then you can see if you can spot. Because I don't think I've taught you adapter. It's one of the ones I've taught you. And I've taught you 3 methods. So let's have a look here. This inherits from a parent. A parent does all the work. It's got the parent's got all the functions that a piece needs. I didn't want to duplicate it for every piece because that's a pain in the bum. So the things that say, I can't even remember all the interface functions a piece had. Can you remember what they were? There were lots of them, weren't there? Okay, all those are in a parent called one-step piece. All the child does is override one function that's defined in one-step piece, replacing it with the characteristics that is specific to that piece. And now when the parent does any of those other functions, which are the interface functions, when it needs to know which direction to move in, it now calls the overridden function that was overridden by the child rather than the default one that was sitting there in the parent. So that's an example of the template pattern. That's right, that's a template. Yeah, they're the only 3 patterns we've seen, I think, so far. Oh no, I mean, you could call MVC a pattern, I guess, maybe. I don't know. But anyway, yeah, template, it's template. So you've seen template, factory method, abstract factory. And template's a really cool factory method to use. You use it all the time. Okay, now we're going to do a bit of admin stuff. Woohoo! So we finished all that stuff that I was going to finish last lecture. The DVD. Someone wanted a DVD of... someone asked for a copy of Richard's lecture. Who was that? Richard Vickery's lecture. I thought I put it in my Bible, but I didn't. I brought a Bible today, by the way. Just in case you forgot to bring one. Did someone ask me? They said, oh, could I see Richard's lecture? And I've been so long putting it up because it was over-quota and I couldn't get it onto my account. But I recompressed it and just put it up before this lecture. So it is up. But someone that wanted to watch Richard Vickery's lecture again, I'll put it on DVD for you. Speak now or not. Okay. Bright, shiny light. Okay. Gary. Well, when I made this DVD, I made a spare one and I gave it to Gary. And he was really excited. He said he wished he'd come along to that lecture, but he was busy making money, sorry. And he got really excited. He loves games, as you know, and he was a bit taken aback by some of the things, I think, that Richard said about Roma. Because, as you know, he likes the game, and Richard was a bit critical of the game, and he was a bit worried. And he's called for an urgent meeting with me tomorrow, and I'll post up tomorrow the results of that meeting. I'm hoping everything's okay. I'm just nervous that he might have had second thoughts about Roma as a game. But anyway, I will post all that on the stop press tomorrow to let you know what arises out of that. Clients. Yeah. And acceptance tests. Don't forget. Actually, someone told me that if you say don't forget, people forget it. I should say don't remember, if that's true. Forget or not forget, as you wish, that the acceptance tests have to be sorted out really fast. By the end of next week is when we make the judgment as to whether we go with your tests or write our own ones. So make sure next week, during the dark ages, you devote your tute and lab to going over acceptance tests together. I'm talking about acceptance tests and programming the project. Every tute's been given some acceptance tests to write, so make sure you knock them together in your tute next week if you haven't written them by now. And the general idea is to try and write something that plays out a game in some way and then asserts that various things are true. So make a couple of moves in the game and then assert the game's now in this state, and then have another game and make some moves and play it. And if everyone just makes lots of those and we concatenate them all together, then you can play other people's game transcripts and check that everything works. Is that cool? So that's got to all be sorted out next week. I'm leaving that in your capable hands. Now, we don't want to burn out poor old Kitten, who's doing lots and lots of work with some other reps, and he had this thing thrust upon him. So please, everyone, help him and jump in and just write some code and do some stuff. Even if you can't work out how to write the code yet, then write some logs of some games. Work out the tests you want to test. You know, every tute should know what cards they're testing. So write a game that involves those cards and checks out some interesting corner cases with those cards. You absolutely want to make sure that you've got good tests. You don't want me to slip some extra tests in that you don't know about. Okay, and that's all. That's all the admin. Woohoo! And then there's a picture of sea change, just for a change. And now, we're talking about designing algorithms and data structures. Woohoo! So, no? Why no? Yes, thank you. You know, designing algorithms, I mean, now we're talking about fun stuff and fooling around and joking. Oh. I don't know why they put that title up there. So, in the first, this is a design course, right? Remember, the thing about a design course is you start off with a problem and you're going to come up with a solution. And in first year, we learn, guys, shh, 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 shh. You three are the terrible three, you're always talking. 5. Man, I was reading someone, they were talking about friendship the other day, and I was talking about friendship, and all these different people have different notions of friendship, and I was Googling around to find out what a friend is and things like that. Just I was interested in abstractly in the concept and wondered if I could share it. And someone said this cool thing, which was they were Jewish, and they said it takes them a long time to make friends. Actually, I think Warren Buffett said this, that someone told him this, so I'm only saying it secondhand. This old Jewish lady told him it takes him a long time to make friends because whenever she meets someone, she has to think, would this person hide me? That's her criteria. It's not like, would they say, I'm your friend on Facebook or something, or would they lend me some stuff? It's, would they hide me? And it's a really big ask. And I did that with Kate last night. We went through our friends wondering which ones would hide us if we needed to be hidden. And now, absolutely, when I said 3, and you said, no, it's 5. It's my other 2 friends as well. Man, that's just so not on. You got to say, it was just me. I am Spartacus. What's that? Oh, you said it.
No, me.
Who did? Yeah, no, he did. Oh, man. Okay, I'm putting some friendship questions in the exam. Okay, I'm going to catch you guys out. So this course is about design, and design is going from a problem to a solution. And in first year, it's just hard enough to move from a problem to a solution. You know, we burn ourselves out in first year just getting to a solution. But now we're in second year, and for the rest of your life, you have enough skills to get from problem to solution. Now you've got to have a neat solution, and a solution that you can make in reasonable time, that's reasonably efficient. And you realise that the client gives you such a big problem, you can never come up with a perfect solution. So you have to make sensible decisions about what to put in and what to leave out. So we've talked about all these approaches to building a solution that mean that at the end of the day, you have something that's reasonably good. you accept you won't have anything perfect. So we're sort of in the land of qualitative stuff now, aren't we? The idea not of just making it right, but making it right and good. And qualitative stuff's always hard. Now we've talked a bit, it's sort of appropriate to talk about design when you see OO, because suddenly in OO you've probably noticed there's a million ways of doing everything. And I remember when I learned OO the first time, well, the only time, when I started learning OO, I haven't finished, I sat down and I thought, oh, okay, I wanted to make a calculator for some reason, an applet. My advice is never ever make an applet, but no one gave me that advice. So I was trying to make an applet. And I wanted to make a calculator applet. You can push buttons and it did calculations and things, because that is so fun. And I was fooling around with it and I suddenly realized, oh, I can do it this way or this way, or this way or this way, or this way or this way. And I was at a caravan park, I remember, and Mum and Dad, we'd gone away on holidays, and everyone was out having fun at the beach, and I was just sitting in the caravan park, not even able to start coding, thinking, oh, I could have this class, or I could have a screen class, and this could, and I just suddenly realized there were 50 million ways of doing it. And as soon as I started programming it one way, halfway through I think, oh, I know, I'll have like individual classes for the keys, and then I thought, oh, I'll have an operation class that these extend, and then, oh, maybe, and I never ever got that damn calculator to work. I was just too paralysed. I went all Sterence, if you remember. I think when you've got so many options, it's really hard to know what to do. So this is exactly when design becomes important. You've got Java, you can do anything, you can write crap solutions, but we want you to write beautiful solutions. So we spent a lot of time over the last couple of weeks, not only teaching Java, but starting to talk about what's a good solution, what's a bad solution, what's a smell, what's an objective we're aiming for, and so on, so on, so on, so on, so on, so on. But that's not the, writing code, coding is not the only way we do design in computing. There's also design in algorithms, in the following sense. When we taught you algorithms in the last course, we essentially showed you a toolbox of existing well-known algorithms. And we showed you some techniques for evaluating and analysing algorithms. So we've given you this sort of basic knowledge. But what we didn't do is tell you how to write your own algorithms, or how to design algorithms. So hopefully you can now sensibly select between a menu of algorithms that someone presents you, and hopefully you know a few already that you don't even have to look up because we've given you some core ones that you can remember. But if you came across a problem and you didn't know an algorithm for it, well, I remember it happened to me. I had graduated from university. I had a computing science degree. I thought I was hot toast, which was a very strange thing to think you were. And then this little kid at a school that I was teaching at came up to me and said, oh, hi, I'm teaching myself some random language. And I've been trying to solve this problem and I can't think how to do it. And you are so clever. So, and you have a PhD or no degree, or you're tall or something. You know all about algorithms. Can you tell me how to solve this problem? And I said, sure, little boy, I will tell you how to solve the problem. What is it? And he said, well, he's running some game, which went on to be a world famous computer game, by the way, and he was really successful. He's over in America now at Stanford or somewhere just doing awesome things. He said, the game it's a puzzle sort of related game, and they're in some pyramid, and they've got some words, and they've got to arrange them into a jigsaw, into a crossword puzzle. So you know the crossword thing, so there have to be intersections, and you can't have invalid things next to each other. Only adjacent things can be words, so it has to be words wherever it's possible to be a word of longer than one letter. And he wanted to have, but he wanted the game to be different every time he played it, so he wanted to generate a random list of words, and he wanted to pack it into a reasonably small space, and he wanted to have it reasonably hard to solve. And he said, how do I do the packing to get it as small as possible? And are there little things I should put to generate the words that are going to make it easier to pack or make the thing easier or harder? And he asked this, and I said, well, that's an interesting question. And I suddenly realized in my whole education at university, no one had ever told me how to solve a crossword packing problem. And I thought, even saying packing problem is sort of giving some hints. No one had ever told me how to solve a crossword problem. And I thought, wow, I've got my degree and I don't know how to do that. And I said, and then, so the only suggestion I could come up with was, can you guess? Reasonable? No, I didn't even think of reasonable guess. Because he wanted to know the best way of packing it. I said brute force. Yeah, I said, well, I guess you could brute force it. And he said, oh, okay, I will. And he thought I was so clever and he went away thinking that's the way to solve the problem. But while he's going away doing that, I'm thinking, if that solves the problem and there's any other way of solving the problem, I've given him the worst. You know, that's only a reasonable solution if there is no other way. I don't even know enough to work out if there is another way of solving a problem or not. I suddenly realized there's a great gap in my knowledge. Given an unfamiliar problem, I had no idea how to even start to come up with a new algorithm to solve that problem or to select between classes of algorithms and so on. And now there's this whole approach to building algorithms, which has been popularized by this really clever guy called Steven Scienna over in America, which is algorithm design. And I want us in the next few weeks now to talk a little bit about algorithm design. So given a problem, you have some sensible ideas about how to start going about ways you might be able to solve it, directions you can head and things like that. And I think that is a design problem just as interesting as the arranging objects and inheritance relationships design problem. And in the same way, there will be many ways of solving the problem. Yeah, like brute force, we'll always do it, won't it, given time. But we want to find the best and we want to know what to do. Okay, so maybe we've already seen a solution to the problem, easy. Maybe we've seen a proof the problem's impossible, easy. But for anything else, we need Mastercard. Okay, so that's what this course is. So brute force, let's just talk about that superly fast. Brute force is, you have a problem that means arranging some elements. You've got some elements in a problem, the problem space, and you've got to arrange them in a certain way to make an element in the solution space. And you want to find the elements in the solution space that satisfy some criteria, like you arrange words so that they intersect where the letters are in common, and so you don't have any adjacent ones, so they the adjacent ones next to each other that don't form words, so that's your constraint. And that's how you arrange them, and you're trying to optimize something often, and so we're trying to find the best packing, the smallest rectangle we can fit it in, or something like that. For any problem like that, it should be clear to you guys after doing 1927 that you could just try all combinations. And you've also, after 1927, should have a fair feel for the complexity of things like that. So even a particular problem, you can have a quick guess and see, is complexity going to kill me on this or not? And if you needed to write the code really quickly and the complexity wasn't too large, then yeah, brute force is probably a great solution because it's going to be really simple, isn't it? You're unlikely to make a mistake in writing it. So, you know, brute force isn't a dumb solution to a problem. But if the problem is likely to grow or change, this change thing kills us again, doesn't it? If the problem's going to grow or get bigger in any way, then brute force is not going to scale nicely because most brute force things will probably be, you know, exponential or super polynomial, probably, won't they? Probably. You know, Murphy being who he is, all that sort of stuff. The adversary's out to get you, unless you can play guitar well or fiddle. So that's all I wanted to say about brute force. Does anyone have any questions about brute force? Woohoo! We've knocked our first topic over already. Brute force. So that's technique number one for solving problems like this. Now your challenge this week is the refactoring, and then next week is the dark ages, nothing happens at all. And then the week after that, the design task is I'm giving you a simple design exercise to solve an algorithmic problem. And you could solve it by brute force, and I'll give you the timings for solving it by brute force. But I want you to come up with a better design. So I want you to come up with something that's faster way of solving it, and by a significant amount faster. So I want you basically to think about it. It's not going to involve any skills that you don't have or things you don't know. This is just an example of rearranging a problem, thinking about a problem, being careful and systematic in the way you go about exploring a problem so you can search the whole solution space more quickly. So it might involve pruning bits of it off that you don't have to, you might realize, oh, well, I never have to look at this because it can't be a solution. Make sure that's true, it's not just a gut feeling if you do ever make an optimization like that. So it's a sort of a fiddly diddly one. I want to see how fast you can go. And I'll tell you what the puzzle is. I sort of half wrote it last week and then haven't released it because we changed the task. So I'll finish it probably on the weekend and release it. But the task is essentially the target problem from the newspaper. You know that one, you've got 9 letters in a grid? And the letter in the middle is coloured a different colour, and you've got to get as many words as possible out of these 9 letters, which all the words have to contain the middle letter, and you're guaranteed that there will be one 9-letter word at least amongst those of the 9 letters, and I'll give you the dictionary you can use to find the words. And I'll ask you how many solutions there are to a problem. And of course you could brute force it, and it's very, very straightforward to brute force. So I want you to do it faster, and to make the speed really obvious, to sort of enhance the hardness of the problem. So differences in algorithms that are a bit faster will sort of yield a reasonably different execution time that we can measure in heartbeats rather than microseconds. I'm going to ask you to go through the dictionary and find the target puzzle that is the easiest target puzzle to solve. So the one that has the most solutions. So basically, find the 9 letters and the letter you'd put in the middle that will give you the 700 possible words you can make out of them, and go through the whole dictionary and check every single possible combination of letters and come up with the one, not one you think is reasonably good. I don't want some heuristic. I want you to come up with the one that has the most solutions. And of course, that's just a precursor to the really interesting problem, which is why I actually wrote the program initially, which is find the hardest one. Because I actually did that and then printed it out and then wrote some crap on the top. Oh, here are some target puzzles if anyone wants to have a go at them. And slipped amongst them the hardest one. And in the dictionary I was using at that time, it had only one solution. There was only one word, which was the 9-letter word. There were no other ones. And my wife, who loves doing them, was going, da da da, oh good. And she was doing some of them, and one of them was the easy one. And she hit the hard one. She goes, yeah. So I want you to find the hardest one in the dictionary. Maybe it's got 2 solutions. Maybe there's none with only one solution. Okay, does that make sense? That's a problem. I'll write it up neatly over the break. But now you know about it in advance. So if you wanted, you could spend some of the dark ages thinking about it, or not, as you see fit. And the last thing to say, and then we'll take our break. Oh, in fact, I better be really fast, because I do want to talk about something interesting after the break, which is an optional lecture, so you don't have to hang around. We keep talking about standing on the shoulders of giants. And remember, I keep musing about this idea of, I have been thinking about it now for more than a week, this idea of iterative design versus the one-off big design up front sort of thing. Maybe I'll talk about it after the break. But what I'm thinking of is, with the shoulders of giants thing, standing on the shoulders of giants means you're sort of using other people's solutions and you're extending them. And that gives you this great power to do amazing things. It magnifies your reach. And it's different to the sort of magnification you get in the avatar sense of putting on an enormous suit and magnifying your power just by sheer stupidity, like running your algorithm on a massively parallel machine so you get a speed up. That's not the sort of idea we're thinking of here. The standing on the shoulders of giant stuff is you combine ideas with other people's ideas, you reuse other people's ideas, and you can come up with new fantastic ideas that build on their ideas. And it's just this really intriguing thing, and I keep thinking about it from different angles. And I was thinking about Beethoven the other day, because I love Beethoven. And we were talking about the Mechanical Turk, and the year the Mechanical Turk came out was the year that Beethoven was born. It was the year that Australia was discovered. Apparently there was no one here already. It was about the time that the Americans had their revolution. There were lots of these interesting things happening, and Beethoven sort of entered this world just after the Enlightenment, and he sort of inherited the Enlightenment. And the Enlightenment was all about people basing things on reason, rather than basing things on faith or doing what you're told or being constrained or constricted by the church or the state or the censors or whatever. And there was terrible censorship in the Dark Ages. It was all about suddenly people thinking, no, all that counts, power should be handed out in terms of reason. It shouldn't be some lady lobs a scimitar at you and you become the king. It should be we reason about it, and the most fit person becomes the king, and they do a reasonable job, and we're constantly analysing what they're doing and thinking about it. So it was suddenly praising reason above tradition and reason above constraint, and it was sort of going against this centralised pyramid sort of thing, and people were climbing on each other's shoulders, and it was just this very exciting time. And ideas of democracy started to appear after so long of disappearing. And I was just thinking about Beethoven. And lots of Beethoven's music, Beethoven loved Mozart. We don't know if he ever got to see him. He certainly tried to see him. We don't know if he ever did. But certainly he based lots of his music on Mozart stuff. And I don't know if you've ever had the same thought, but if I had a time machine, I think, if I went back in time, has anyone seen Back to the Future? Okay, I couldn't believe that it's in Back to the Future, so it makes me think maybe this is a meme that everyone has, because it was in Back to the Future. Michael J. Fox goes back in time and then plays a guitar riff back in the 50s or sometimes. And it was just before rock and roll, or just the time of rock and roll, 60s. I don't know, details. And everyone's blown away, and everyone's going, wow, because he's playing modern music. And the modern music is like 80s music, okay? You know, we look at it now and we laugh. But then it was the latest thing. And I often think that about music. I think, would the people back then have even understood it? Like, would they have liked it? Would they have gone, oh, wow, that's so cool. Born to be Alive. I can't believe how good that is. Would they even understand that? Because maybe you need all the stuff that's happened before it to get in the context of even being able to understand or interpret the music. And it just suddenly made me realise how music, like maths, and I'd always known about this about maths and all the fields I like, but music must be like it too. Ideas must build on ideas and ideas and ideas layer on it. And so when you do something, the audience has been prepared with the other ideas they've seen and heard. And so I often think, what would Beethoven do? Like if he was born before Mozart, his music would have been quite different because he wouldn't have had Mozart to borrow from. What if Beethoven was around now? Like what would he have drawn on? Would he be like Eddie Van Halen? Would he be doing this amazing stuff? Or would he, you know, because what's important about Beethoven is the ideas he had, the design he did, not the constraints. So in different periods of time, he'd have different constraints. What would happen? So I think about this all the time. I can't really even articulate what it is I'm thinking about, but somehow, to what extent are ideas emerging and evolving and depending on previous ideas, and to what extent are they independent and have value and just stand by themselves? I think there's a lot of this evolution, this incremental thing going on. So I just wanted to play this little bit of music of what I think Beethoven would do now, if he was around now. And that'll be our break. He's a very strange looking boy. You don't have to watch this, by the way. You can just move around and stretch your legs and things.